Okay, great. I think I'll make a start now. So welcome back, everybody. Nice to see so many of you on the session today. So today I'm going to start off talking about synchronization constructs in OpenMP. And then the second talk is a little bit of a odds and ends collection of other useful stuff. So as before, please feel free to type questions in the chat feature. So if you're new to Collaborate, get to that by clicking the purple arrows at the very bottom right of the window, and then click on the speech bubble, and then type in the box at the bottom of the side window. So I will stop at various points and invite questions, but please feel free just to type away as we go along. I'll keep an eye on for any questions coming in. Synchronization then, just remind ourselves why it's required. So when we're inside an OpenMP parallel region, we have threads executing asynchronously by default. So we need to synchronize actions on shared variables inside the parallel region. We might need to ensure, for example, correct ordering of reads and writes, to be able to make sure that one thread really has written some variable before another reads it. And there are also other patterns, such as the need to protect updates to shared variables, which are not atomic, are not single indivisible actions by themselves. So let's look at some of the mechanisms we have available in OpenMP. The first of these is the barrier directive. So this is a full synchronization point between all the threads in the parallel region. No thread can proceed past the barrier until all the other threads have arrived. And we've already discussed this a bit because there are these implicit barriers at the end of the work sharing directives. So like OMP do, OMP4, also sections, which I'm not going to talk about, and single directives. So the syntax is very straightforward. It's just the barrier directive. There is no associated block of code with this one. And something we might need to take care of is that if we have some complicated control flow inside our parallel region, we need to make sure that either all threads or none of them encounter the barrier. Otherwise, that will result in deadlock, because if some strict subset of threads get to the barrier, they will wait forever, waiting for the ones that never get there. And this is also true of the work sharing directives as well. So for the same reason, if we have a work sharing do or for or a single, then we have to make sure that either all the threads in the parallel region reach that point or none of them do. So it's slightly tricky to contrive an example which will fit easily on a single slide, but let me try anyway. So the situation I'm supposing here is that I'm organizing my threads in a ring in some sense. So inside a parallel region, and every thread reads its own thread ID. So it calls OMP get thread num, stores that in my ID. And then every thread has a notion of its neighboring thread. So my neighbor is, say, my ID -1, except if I'm thread 0, then my neighbor is the last thread. And then I do some computation, and as part of that computation, I use my thread ID to index into this shared array A here and write some value into it. And then some point later, I want to be able to read the value that my neighboring thread wrote. So I have one of these cases here where I have a potential race condition unless I do something to make sure that the writes and reads are correctly ordered here. So one way I can achieve that is with a barrier here. So if I put a barrier in between the write and the read, that makes sure that all the threads have written here before any of the threads try to read a value that a different thread wrote here. Okay, Alessandro asked, if I have a thread that spawns other threads, how does the number of threads that the barrier checks to pass? Okay, so this is really a question about nested parallelism, which I will talk about later on. Okay, so the only way to spawn threads is in OpenMP is with nested parallel regions. So you can't just arbitrarily create other threads when you want to. So the barrier directive always applies to the threads in the innermost enclosing parallel region. And so if I have nested parallel regions, the barrier binds only to the innermost set. Okay, there's no way to have a barrier across outer parallel regions. So that's it's a little bit of a potential problem when you come to coding with nested parallelism, but I'll talk a bit more about that later on this afternoon. Okay, so just for any Fortran programmers that we have today, here's the same example in Fortran. So again, I read my thread ID, set up my neighbor, write some values into this shared array A, synchronize all the threads, and that makes sure that all these reads of my neighboring value will get the right value here. Another example, we remember from last time, if you have a master construct, master does not have an implicit barrier. So if you want to synchronize the threads after a master region, so thread 0 does something, all the other threads skip over it. If you want to synchronize at the end of a master, then that would be another case where you would want an explicit barrier directive. Any other questions about that? What is the my ID equals 0 syntax? Okay, this is Fortran. So this is just if that's fairly old-fashioned Fortran, or just for an equality test. It says if my ID is equal to 0. Oh, okay. Yes, that's my cut and paste error. Oops, sorry about that. Okay, so move on to the next type of synchronization, which is critical sections. So a critical section is a block of code which can be executed by only one thread at a time. And this is what we want to be able to protect updates to shared variables. Make sure that only one thread at a time can execute a particular piece of code. So no particular surprises with the syntax here. So Fortran, it's OMP critical, followed by a block of code, and then end critical. And for C or C++, hash private OMP critical, followed by a structured block. So example I'm going to use here is supposing that we want to do some calculation and then append some items to a shared list. So I have some data structure, which is a list here, and what I've actually got here is this data structure, which is shared between all the threads. Okay, so imagine here I've got a parallel loop, okay, and then in every iteration of the loop, then this create item function returns a pointer to a new item. Again, I've got more typos in here. I'm doing badly today. Okay, this is supposed to be the same as that. So, and then what I want to do is I want to append that new item into the shared list. So I'm going to assume that this append function is not internally synchronized in any way. So it's just plain old sequential code. And therefore, most likely, if two threads call that at the same time, there's going to be some internal race condition and bad things will happen. The list will get corrupted in some nasty way. So what I can do is enclose this append call inside critical, and that will mean that only one thread at a time can enter this block of code and do the append. So Kevin asks, is it first come, first execute for threads hitting the OMP critical section? Yes. Yeah. So whichever thread gets there first will go ahead and execute it, and then other threads have to wait. We also have some guarantee of fairness as well, in the sense that if you have lots of threads repeatedly accessing a critical section, then you are guaranteed that they will all get in at some point. And so you have some guarantees about fairness there. So critical doesn't do any ordering, okay? So we have no idea which order the threads will execute it, just as it happens one at a time. Okay, so in the exact case of a loop, how is this better than one thread doing the loop? So in this case, so that depends on really the relative execution times of this function, okay, and this append. Okay, so if this create item function is really expensive compared to this, then I will get some useful I will still get some useful parallelism. Okay, good. And this the same deal in Fortran. Same idea. Good. So slightly more complicated example here. Now, suppose instead of a list that I'm just going to append to, suppose I actually have a stack which I can both pop items off and push new ones on. So again, parallel region, and then I'm going to have here, so slightly different example, I have a while loop. So while I'm not finished, while each thread is not finished, it's going to pop the stack and get a pointer to an item. It's then going to do some processing on that, and that may return a pointer to a new item. So if that's a valid pointer, then I want to push that new item onto the stack so that it's available for other threads to pop and execute. Okay. And I'll finish when the stack is empty. Okay, so again, I'm assuming that this shared stack data structure here needs some protection from multiple threads trying to access it at the same time. So in this case, I need to protect both the pop and the push functions. And the semantics of OpenMP critical means that I can just do it like this. So if both the pop and the push are inside critical sections, that guarantees mutual exclusion from the stack data structure. Because the way OpenMP criticals work, if one thread is in this critical section, then it means that not only can no other thread also be executing in here, then no other thread can be executing in this critical section, or indeed any other critical section that happen to appear in this parallel region. Okay, so so Robert asked, if the critical sections were named, would the mutual exclusion be lost? Yes. Okay, so didn't actually mention that, but seeing as you've brought it up, it is possible to give a critical section a name, and in that case, if these two critical sections have different names, then they do not mutually exclude from each other. If they do have the same name, then they do mutually exclude from each other, and that's also true if they don't have any name at all. Okay. Same example in Fortran as well. So next up is atomic. So in some respect, atomic is like a special case of critical, because it's used to protect a single update to a shared scalar variable of basic type. So and when I say scalar, that can include array elements as well. So it applies only to a single statement, and that statement must have a certain form. So essentially, that it must look like an update. So more specifically, in Fortran, we have OMP atomic followed by the statement, and that has to look like x equals x operator some expression, or the other way around, or we can have intrinsic functions here. So things like x equals max of x and something will also work. Similarly, in C and C++, hash pragma OMP atomic. So the form is slightly different here because of the different underlying syntax for the base language. So the statement here looks like x binary operator equals something, or things like x plus plus or x minus minus. One important difference from critical, however, is that the evaluation of the expression on the right-hand side is not protected, is not done atomically. So it could be that the evaluation of this expression, say, could involve some function calls, which in turn might involve some modifying some shared variables, some shared state. Atomic does not guarantee or does not enforce mutual exclusion from anything that's happening on the right-hand side. The only thing that's protected is the update to the variable on the left-hand side. So an example might be, suppose the expression here was a call to a random number generator. And so most random number generator functions include some update to some shared state internally. So that wouldn't be something like that would not protect you from having multiple threads trying to access or execute the random number generator function concurrently. So the point of this is that there are opportunities for the compiler and the runtime to make this particular special case significantly more efficient than using critical. So in particular, if you'd like to think about the difference, is that while critical is providing protection from threads executing a block of code, atomic is providing protection from threads updating a particular memory location. So critical protects code, which may indeed protect memory locations implicitly, whereas atomic explicitly protects a memory location. So this may be more efficient, particularly if for example, and I'll show you an example in a minute, if the thing on the left-hand side is an array element, then it's possible to have, using atomic, to have concurrent updates to different array elements going on at the same time, whereas that wouldn't happen if we used critical. And it's also important to remember that there is no interaction between atomic and critical. So you try to protect and access to a memory location using critical in one place and atomic in another. That does not work. So critical and atomics don't mutually exclude. Can you give a name to atomic too? No, you can't. You can't name an atomic. Okay. So if you like, one the other way to think about it is that atomics are sort of named according to what the address of the thing on the left-hand side is. Okay. So if the thing on the left-hand side is different from different atomics, then you get separate exclusion. So atomics only mutually exclude if you're actually trying to update the same memory location. So I'm trying to think. I don't think there would be because of that property, I don't think there would really be a good use case for naming atomics. Good. So my example here is I want to compute the degree of every vertex in a graph. So okay, so here's a simple graph. So the blue dots here are the vertices, and the red lines are the edges that connect the vertices together. And the degree of a vertex is just the number of edges that are connected to it. So this vertex has degree 1, for example. This vertex has degree 3. So the computation I'm going to do is I'm going to have a loop that runs over all the edges in the graph, and I'm then going to add 1 to the degree count for the vertex at either end of that edge. Yeah. So here's my loop. So, okay, loop over all the edges. Then for the jth edge, contains an index of the vertex at one end, and use that to index into an array of degrees and add 1 to it, and then do the same for the vertex at the other end of the jth edge. So obviously this is a tiny graph, but you can imagine that be doing this for a very large graph. So I could have, say, millions of vertices and millions of edges going on here, in which case it might be worth executing in parallel. So this is a case where using critical just wouldn't help, because I would have to enclose both these updates here in a critical. So it could be in separate ones, could be in the same one, it doesn't matter. But whichever way I did it with critical, it would mean that only one thread at a time could be updating any element of that array. So that would remove all the parallelism from this problem, and in fact it would go slower than the sequential version because of the overheads of the criticals. However, if I use atomic, then it at least gives the implementation the opportunity to protect updates to different elements of the degree array separately. So hopefully I will get, again, there's still some overhead of doing the atomic accesses possibly, but I will at least get some parallelism, because most of the time the threads will not be trying to update the same elements of degree at the same time. So most of the updates will be disjoint ones. So Alessandro asks, isn't equivalent except for the atomic optimizations to two criticals? Yes, it is. Yeah. Yeah. So in fact, it is legal for an OpenMP implementation to replace or to implement the atomics as criticals. So in that sense, they are absolutely equivalent. However, you would hope that most implementations do something better than that, but you can't absolutely rely on it. Okay, any more questions about atomics? Good. So the last topic in this session is the lock routines. So critical and atomic cover, I would say, the vast majority of use cases where we want to protect updates to shared variables. But sometimes we need more flexibility than is provided by critical or indeed atomic. So OpenMP provides what's really a very classical set of mutex lock routines. So this is the usual idea for mutexes. A lock is a special variable that can be set by a thread, and then no other thread can set the lock until the thread which did set it has unset it. In OpenMP, setting a lock can either be blocking or non-blocking. So a thread can either attempt to set a lock and wait until it's available, or it can attempt to set a lock and return immediately with a true or false value as to whether the set succeeded or not. You have to initialize locks before you use them, and you can also destroy them again when you don't need them anymore to free up any resources that might be associated with them. The lock variables themselves are not supposed to be used for any other purpose. They're intended to be opaque types, and you're not supposed to store any data in them. So in reality, they're probably just plain old integers, but you're not meant to know that or try to store any values in them. So for the Fortran interface, and this comes from the OMP lib module. So we have the init call to initialize the lock, and Fortran defines a lock kind that you should use to declare your lock variables. The set lock, so set lock is the blocking set. And very confusingly, I think this was a poor choice of naming. OMP test lock is the non-blocking setter, which is not really what you expect from the name. So test lock does not do what you think, which would be to say, is this lock currently set? it says, please set this lock and return true or false, depending on whether you succeeded or not. Then we have the unset and also the destroy. And pretty much identical set of 5 different routines in C and C++. So again, OpenMP defines a type for you to declare these things with. Okay, so suppose I have my same example with my graph problem again. So I could potentially also solve this with locks. In this particular example, it probably doesn't make sense because atomic would be more efficient. But there might be other circumstances. Suppose that this update was actually something more complicated, and what appeared on the left-hand side here was not actually a basic type, but some data structure or an object or something like that. So in this case, I could declare an array of locks and initialize them. And then in this case, I would choose, the number of locks to correspond to the number of vertices. Okay? I don't have to do that. That would just be one way of doing it. But what I can do is, so if I have exactly one lock corresponding to every vertex, then whenever I want to update a particular element of this degree array, then I would set the corresponding lock, do the update, and then unset it again. And then the same for the other vertex. Okay, so this is a rather artificial example, but this pattern particularly tends to crop up in molecular dynamics type simulations. So in that case, instead of having vertices and edges, I have particles and force interactions between them. So typically you need to compute force interactions between pairs of particles and then update the total force on the particle at either end of the interaction. So you can end up with very similar patterns in that case. So the associated practical exercise with this is, in fact, yes, a very simple molecular dynamics simulation. And so in this case, you can try using all these different forms of synchronization, actually. So you can try it with, what I suggest you do is start off with critical sections, and then try using locks or atomics. Well, there is actually also another possibility here for this particular code is to use reduction arrays. So there's lots of different ways you can solve the same problem, but they may perform differently, and that may also depend on how many threads you're using. Great. Anyone have any more questions? Very well. So I suggest we give ourselves a break and resume at 3 o'clock. UK time, so 15 minutes. Okay, hello again, everybody. So this session is some further topics. So it's a little bit of a disjoint collection of things that I think you also ought to know. So what I'm going to cover in this session is nested parallelism, and as advertised earlier, orphaned constructs. Okay, so that's to do with the way that data scoping and shared and private variables work in the context of function calls and subroutine calls. I'll say something about thread private global variables, something of a necessary evil, really, and then a word or two at the end about timing routines. Okay, so nested parallelism is supported in OpenMP. So what happens if we're already inside a parallel construct and we encounter another one, then a new team of threads will be created. Typically, this has to be enabled, so either with the OMP nested environment variable or the OMP set nested routine. So most implementations have it disabled by default. It's not that often needed. It can be useful if you do have a hierarchy of parallelism in your application and the outer level doesn't contain enough parallelism to keep all your threads busy throughout the lifetime of the program. As I say, usually disabled by default because implementing it introduces some additional overheads in the runtime. So don't turn it on unless you're actually using it. If nested parallelism is disabled, then your code will still execute, but what will happen is those inner nested parallel regions will only contain one thread. So those inner parallel regions will still execute perfectly happily, but they won't create any additional threads. They'll just be executed by the thread that encountered them. Okay, so it allows you to do things like this. Yeah, simple example. Okay, so suppose I have two loops here, two nice simple parallel loops. An I loop that writes some values into array X, and a J loop that writes values into array Y. And those loops themselves are completely independent. So what that allows me to do is to have them both executing in parallel themselves, but also in parallel with each other. So what I could do here is have an outer parallel region. So it's my outer parallel region, parallel and end parallel. And then I simply say, okay, and suppose I'm going to arrange that this outer parallel region has two threads. I'll talk about various ways of arranging that and controlling that in a minute. But let's just for the moment assume that I can arrange that this outer parallel region has exactly two threads. Then, so thread 0 will execute the X, the I loop, updating X, and if I put a parallel do here, then I will get a new team of threads created. And at the same time, then for the other thread, for thread 1, the other outer thread, it can also create a new team of threads to execute the J loop. So I get a pattern something like that. I have the original master thread, the outer parallel region spawns 2 threads, creates 2 threads, team of 2 threads. One of those threads then creates a new team that shares out the I loop. At the same time, the other thread creates a team to share out the J loop. Okay, so we have a number of different options for controlling the number of threads in nested parallelism. We can actually, for some cases, just use the environment variable. So the environment variable OMP num threads, which normally used to control the number of threads, will actually take a comma-separated list of values. So this specifies how many threads at the outer level, and then how many threads at the next level down, and then I can keep going. I can have more levels if I want to. So, but if I say 2,4 here, then that will use 2 threads at the outer level, and then 4 threads for each of the inner teams. So that's okay as long as I actually do want the same number of threads for all of the inner teams. There are some other mechanisms. So there is also a OMP set num threads routine and a num threads clause on the parallel region. So both of those can also be used to control the number of threads. And let's see how that can be done. So these are useful if you want, for example, the inner regions to use different numbers of threads. Here's a slightly more complicated example. Yeah. So suppose I have an outer loop with 4 iterations in it. And I'm going to use 2 threads to execute that outer loop over 4 iterations. So I can, in the master thread, I can set the number of threads called OMP set num threads to be 2. And that will cause this outer parallel region to be executed by 2 threads. And so each of those threads is going to get 2 different I values. And for each different value of I can then also call OMP set num threads and pass some values that I've already pre-computed and stored in an array somewhere. So not only can every thread inside the outer region use a different value to spawn the inner parallel region, but indeed every instance of this inner parallel region could potentially use a different number of threads. So the way this works is, and it's perhaps a little bit easier to understand what's going on here, is that OpenMP has some internal state which are called internal control variables. And these control various different things in OpenMP. But one of these internal control variables is used to determine how many threads will be used by the next parallel region. And every single thread has its own copy of that internal control variable. So every thread has its own notion of how many threads it would create if it encountered a parallel region. And essentially, OMP set num threads is the setter routine for that internal control variable. But confusingly, as we saw before, OMP get num threads is not the corresponding getter routine. OMP get num threads says how many threads are executing in the current context. the getter routine for the internal control variable is actually called OMP get max threads. And I'll talk about that again on Thursday. If you do use OMP set num threads routine, then and you modify the internal control variable, then that overrides what you set in the environment variable. So the environment variable gives that internal control variable an initial value, which you can then override by calling the corresponding setter routine for it. Alternatively, you can use the num threads clause. So this is a clause that appears on the parallel construct and also can be used to set the number of threads. And that in turn overrides anything that was set in the environment variable or by previous calls to OMP set num threads. So which you use whether you use the OMP set num threads or whether you use the num threads clause, something of a matter of taste, might depend on the context. So the num threads clause is a little bit clearer in some sense in the code because you can look at a parallel region and know how many threads it's going to use without having to sort of trace back through the code and figure out where the last OMP set num threads call was. On the other hand, this may be inconvenient if you don't want to pass these kind of values down all this way down the call tree. If you're implementing something like a library, then you might want to be able to control the number of threads from outside the library rather than by passing stuff in. So again, depends a bit on the context and partly a matter of taste which one you use. Also have a bit more control. So with nested parallelism, it's very easy to end up creating an awful lot of threads, and you probably don't want to create more threads than you have hardware resources. So that might be cores, that might be hardware threads. So you can set an upper limit which controls the maximum number of threads that are running at any one time. And that's an environment variable called OMP thread limit. So for example, if I was running on a system with 64 cores, I could set OMP thread limit to 64, and that would guarantee that there are never more than 64 threads active at any one time. You can also control the maximum depth of nesting that's allowed. So you can set an environment variable or make a runtime library call to affect the number of active levels of parallelism. So below that depth of nesting, the code will still work, but nested parallel regions will execute on a single thread. And then there's a bunch of utility routines that tell you something about the current context. So, okay, this question from Nicholas. Is it good practice, generally speaking, to have threads with more serial work each, or threads that spawn inner threads with less serial work each? So, I'm not quite sure I understand the question. It's typically better to exploit the outer level of parallelism as much as possible, and only go to inner levels when you don't have enough parallelism, or perhaps the outer level really isn't very well balanced. But if you have load balance problems, then actually there are possibly better ways of handling that. Trying to do load balancing by creating teams with different numbers of threads is a bit of a crude mechanism. Oh, good. Did answer your question. Excellent. Okay. Yeah. So if you have complicated nested parallelism with load balance problems, then actually nested parallelism may not be the best solution. So instead, you would probably want to use tasks and nested tasks to handle that, because it's much more flexible in the way that it does the load balancing. But I'm not going to talk about tasks in this course. So don't have one scheduled at the moment, but imagine in not far distant future we'll be running the advanced OpenMP course, and that does cover tasks if you're interested in that kind of thing. Let's say that's the general advice. There may be good cases for why you want to push work down to lower level parallelism, which might be to do with data affinity. So if you have a very natural data decomposition type problem, then you might want to have groups of threads in an inner region all working on the same piece of data or the same part of the space. So that there are potentially other reasons, but by and large, you want to try to exploit the outermost level as much as possible, because that will tend to minimize the overheads of parallel regions and so on. Okay, so Alessandro, so can a thread control, affect, or kill another thread? Okay, no. So in OpenMP, you don't have that kind of power. Okay, so there's no way to kill threads. Okay. Yep, no time traveling. Yeah, so yeah, your threads compared to some other compared to other APIs like P threads or C++ threads, you have fairly limited powers of creation and destruction in OpenMP. So the only way to create threads is with parallel regions, which includes nested parallel regions. And there's essentially no way to kill them. They will keep executing until the end of the parallel region. And there is a mechanism to do premature termination of parallel regions. So for example, if you have something like a search problem, okay, and you want the first thread that finds something to stop all the other threads executing, then you can do that, but they don't die, they just skip straight to the end of the parallel region. So you don't have this ability to create and destroy threads at will. So what happens if a thread gets stuck? How do you regain control? Basically, too bad, you don't, okay? Yeah, that is a problem, okay? Or at least it's a limitation of OpenMP. So You can always exit, okay? That's the, any thread can call exit, and that'll take out all the other threads in the program. So if you have to die, then the whole program and all the threads need to die. But it's so you can do that, but it's all or nothing. Okay, good. So these utility routines. So get level returns the level of parallelism of the calling thread. So and it also returns, that'll return 0 in the sequential part of the program. So we call it on the original master thread, that returns 0, and then 1, 2, and so on as you go down the levels of parallelism. Get active level does the same thing, but it ignores any levels which are inactive. So inactive means they consist of teams with only one thread in them. Okay. Okay, and then get ancestor thread num at a particular level, returns the thread ID of this thread's ancestor at a given level. So what happens, what returns get ancestor if you're in the master? So if I think if it turns get, that's a good question. I'd need to look that up. I think if you're in the master thread and you call get ancestor thread num at level 0, I think you'll just get 0 back again. But I'm not I'm not sure about that. Yeah, I think so. I think you call it get ancestor thread num at your own level, then you just get your thread ID back again. So if you want your, say, what you might want is, say, the thread ID of your parent, then you would call OMP get level, subtract 1 to go 1 level up, and then call get ancestor thread number at that level. And then you can also get team size at levels above you as well. So thread numbers always start from 0 in every team. And so there is no global thread number going on here. Okay, so there's one particular use case where there is a better or at least cheaper mechanism for handling it rather than nested parallelism. So if we have so-called perfectly nested rectangular loops, so we have a pattern like this. So we have, say, for int I equals 0, I less than n, immediately enclosing for int j equals 0, j less than m, and then possibly more loops inside as well. Then for this particular case, then if you want to parallelize more than one loop in the nest, you don't need to use nested parallelism. What you can do is you can use the collapse clause, which applies to the work sharing for or do directive. So what does perfectly nested rectangular mean? Okay, so perfectly nested means that there are no statements between the loops. And so there's no code in here or no code in here there's no code between the beginning and the end of the loops. Rectangular means that none of the bounds of the inner loops depend on the iterators of the outer loops. Okay, so I could not, for example, have, if I had j less than I here, that would not be a rectangular loop, and that's also not allowed. So the argument here is the number of loops to collapse, counting from the outside. So if I want to parallelize both the I and j loops here, then I use collapse 2. So what this does is that it will transform this nest of loops into a single loop. So in this case, that single loop will be of length n times n, and then it will schedule and parallelize that. Okay, so it'll create this implied long loop, and then just treat that like a normal parallel for loop. So this can be useful in some cases, so for example, if n is of the same order as the number of threads, then you might not get good load balance. Or if n is less than the number of threads, then you might want to exploit some additional parallelism from the J loop as well. So for this particular case, that's typically much more efficient than doing it with nested teams. So Milena asks us, what if it's not a perfectly nested rectangular loop? Say parallel 4 plus SIMD. Okay, if it's not a perfectly nested rectangular loop, then you might have to resort to nested parallelism, or possibly to do code rewriting. You have to remember that you can have remember that you have to remember that SIMD here is a different sort of parallelism in the hardware. So SIMD loops are not creating threads. I'm not going to talk about SIMD in this course, but SIMD is just for vectorization, so it does not involve thread parallelism. Alexander says, guess you can collapse perfectly nested cubic loops with collapse 3. Yes, absolutely. Okay, so in principle, I think you can go as far as you like. Okay, you can, yeah. It's just so that you can have as much control as you want. For example, you might have a triply nested loop, but the innermost loop was actually sequential, in which case you would only want to do collapse 2. So you don't necessarily want to collapse all the loops in a nest. Good. Okay. Then if we have nested parallelism, we also have to think a little bit carefully about how the synchronization works. So, example, I talked a little bit about earlier. So barriers, so either explicit barriers with a barrier directive or implicit ones with work sharing directives, they only affect the innermost enclosing parallel region. There's no way to have a barrier across multiple teams. On the other hand, critical regions, atomics, and locks affect all the threads in the program. So if I have, say, a critical section, then that's mutual exclusion from any thread anywhere in any other parallel region as well as the current one. So that's a bit of a problem because if you want mutual exclusion within an inner team but not between them, then you need to use locks or atomics. You can't use critical anymore, because critical really does behave like a single global lock. Okay, any more questions about nested parallelism? All right, let's talk about orphan directives then. So the concept here is quite straightforward. It's just that directives can be present in functions called from inside parallel regions. So if I have a parallel region that makes a function call or a subroutine call, then it's perfectly okay to have something like, have work sharing directives inside the subroutine. And so every thread is going to call this subroutine, and then this indicates that the loop iterations get shared out between the threads. So that all works fine. The tricky bit is to do with data scoping, which I'll come on to in a minute. Okay, so this is really nice because it's it doesn't break your modular programming style. It can be a little bit confusing if the call tree is complicated. So what happens? You have to think a little bit carefully about what would happen if I called Fred from the master thread, okay, from outside the parallel region as well as inside it. And it turns out that's basically okay, because the work sharing directive does not create threads, and so it will simply, the master thread will simply execute the whole loop if you do that. Okay. And likewise, as you said, if you have any synchronization construct in there and you call it from the master thread, it effectively just ignores them. So that's okay. Need, however, some extra rules about data scope attributes, about shared and privates and so on. Okay, so if we call a subroutine function from inside a parallel region, then the variables in the argument list inherit their data scope attribute from the calling routine. So essentially, if it was shared in the parallel region, we pass it in, it'll be shared inside. If it's private in the parallel region, we pass it in, it's private inside. If we access global variables, or Fortran, things like common blocks, if anybody ever uses them anymore, or module variables, so any sort of global variables, those are shared unless we do something special called thread private, which I'll come on to in a minute. Local variables that are declared inside the function or subroutine. So if they have the static keyword in C or C++, they are shared. If they have the save attribute in Fortran, then likewise they are shared. But all other local variables are private. Yep, so thread private global variables. So I would say that this is kind of a necessary evil in the sense that it's probably good practice never to design this into your code if you have the opportunity to do the design. And it just is convenient to handle the way that some existing codes may be written. And avoid a lot of refactoring. But it's not really it's not a nice thing, okay, from a software engineering point of view. But sometimes it is just the most convenient thing to do is to give every thread its own copy of variables with global scope. Okay, so again, common blocks, module data in Fortran, file scope or namespace scope variables in C and C++. So if we do this to this type of variables, then outside parallel regions, so in the sequential part of the program and in master directives, then any accesses to those variables refer to the master thread's copy of them. So how do we do this? Okay, so this is a directive that belongs together with, essentially together with the declarations. So in Fortran, we can do OMP thread private and then a list of things, okay, where things may be common blocks or module variables or variables with the save attribute. And that has to come after all the declarations of those variables. Similarly for C++, the directive must be at the file or namespace scope. It must come after all the declarations and before any references to the variables that are in the list. Okay, and there's a few other restrictions you have to take care of as well. And then also, if you need it, then there is a copy-in clause that applies to parallel regions. So what that will do is at the start of the parallel region, it will copy the value in the master thread's global variable into all the other threads' copies. Okay, any questions about that? So say it's not a nice thing. You should probably avoid it if you can, but just to deal with the way that some codes are written. So if you have some kind of temporary or scratch variables that are declared as globals that are used way down the call tree somewhere a long way down inside a parallel region, then trying to untangle that and pass private copies around or try to replace variables with arrays and index them with thread numbers or all that kind of thing just can be unbearably messy. So, so there are cases where thread private is just the simpler solution. And finally, just a word about timing routines. So OpenMP supports quite a handy portable timer routine. So this is called OMP get W time, and it just does the usual thing. It returns the current wall clock time relative to some arbitrary origin. And so, two nice things about it. It really is wall clock time. So you do have to be careful with other timers that you're not measuring accumulated CPU time across all the threads or something else. Okay, so at least you aren't guaranteed that it's genuinely wall clock time. And also it returns a double precision value in seconds. So it typically saves you from any horrible conversions from some structure of seconds and nanoseconds or something nasty that you have to deal with. So it's quite convenient. And you can also ask the implementation what the precision of the clock is as well. So you don't have any guarantees. So different implementations may provide different clock precisions, may depend on the hardware and the operating system. So, but you can ask. On the whole, most implementations of this are pretty good. You get sort of at least a microsecond resolution, possibly better, and also the overheads tend to be pretty small. So it's quite a nice interface for timing bits of your code. So you just use it in the usual way. Call it once, store the result, do the thing it is you want timing, and then call it again and take the difference. In principle, timers are meant to be local to a thread. So in order to get a meaningful result, then these two calls need to be done by the same thread. As I say, you don't have any guarantees about the resolution, but you can at least ask. And the practical exercise that goes with this one is to go back to the molecular dynamics one again and explore the use of orphan directives. So you can essentially, instead of having a parallel do or parallel for directive, try separating out the parallel region and move it out into the calling routine, and making everything else sequential. But don't expect that to change the performance very much. It won't make much difference to the performance. But the idea here is it's just a useful way of seeing how that affects the data attribute scoping. Okay, so how that changes the way that you need to declare things. And there's at least one nasty little gotcha with that, which you can look out for. So if you do this, then there's the potential for having harmless-looking race conditions that aren't actually harmless at all. Okay? So OpenMP specification is quite strict about race conditions. It says that any such, it says essentially there's no such thing as a safe race condition. So even though you may have every thread writing the same value to a shared variable, that's still considered an error, strictly speaking, in OpenMP. And it can also have some nasty performance consequences as well. I certainly worked, not that long ago, I worked on a commercial piece of code that essentially made that mistake. So there were some variables inside a parallel region, inside a parallel loop, where every thread wrote the same value into those variables and then used them. So it always gave the same results. Never got the wrong result, but the performance was horrible because you get a lot of cache line thrashing like that. And simply by making them private instead, you get much better performance. So even if it's not, even if they look harmless, like they're like you're never going to get the wrong answer, then you can still get some nasty performance side effects from having benign looking race conditions in your code. So watch out for those. Okay, any more questions for today? Good. So I see several of you have signed up for Cirrus accounts. It's certainly not too late. If you still want to do that, absolutely no problem. And if you want any help or support with the practical exercises, then please let me know, say either through the chat board or directly by email. So if you just want me to, even if you just want me to check that what you've done looks sensible, that's absolutely fine. Just drop me an email with your code, and I'm very happy to take a look. So that's really pretty much all the OpenMP features that we're going to cover in this course. So the final session on Thursday will look at practical tips and tricks, things to watch out for, useful odds and ends that will hopefully make your life as an OpenMP programmer easier, and avoid some of the nasty things that can trip you up and waste a lot of your time. And then we'll also look at performance considerations. OpenMP is a nice interface in the sense that it's quite easy to use, and it's reasonably easy to implement something that works correctly, but getting good performance is not always straightforward. There's a lot of things that can go wrong and prevent you getting good performance. So we'll talk about that on Thursday. In the meantime, thank you very much for coming along. Hope it's been a useful session for you.